Welcome to my project bazaar. We are going to see the product high performance FIR filter architecture for fixed and reconfigurable applications. Now we are going to see the abstract for our product. The power consumption and speed are the two main challenging factors in very large scale integrated circuit design techniques. The consumption saving is one of the way to obtain the optimized power consumption and speed. The design of finite impulse response filter using transverse form structure is naturally pipeline and upholds multiple constant multiplication technique. This MCM technique results in large computation shaving, but the transverse form configurations are not supporting the block processing. In the existing method, the possibility of realization of FIR filter transverse form configuration to achieve efficient area and delay for large order FIR filters were a filter is a device or process that removes some unwanted component or feature from a signal, filtering a class of signal processing. The defining feature of filter being the complete or partial suppression of some aspect of the signal. There are two main kinds of filter, analog and digital. Filters can be classified in several different groups depending on what criteria are used for classification. FIR filters are one of the primary types of filters used in digital signal processing. FIR filters are said to be finite because they do not have any feedback. Therefore, we send an impulse through the system. A single spread, then the output will invariably become 0 as soon as the impulse runs through the filter. A non-recursive filter has no feedback. The finite impulse response filter has no feedback. Based on a detailed combinational analysis of transverse form configuration of FIR filter, they have derived a flow graph for transverse form block FIR filter with optimized register complexity. A generalized block formulation is presented for transverse form FIR filter. They have derived a general multiplier based architecture for the proposed transverse form block filter for reconfigurable applications. The implementation of direct form structure has less area delay product and less energy sample for the short length filter. There are several applications where the coefficients of FIR filters remain fixed, while in some other applications like STR channelizer that requires separate FIR filters of different specifications to extract one of the desired narrow band channels from the wide band RF front end. These FIR filters need to be implemented in a RFIR structure to support multi-standard wireless communication. Next we are going to see the flow diagram for our product. The block processing method is popularly used to drive high throughput hardware structures. It not only provides throughput scalable designs but also improves the area delay efficiency. In our flow diagram, we give 4 bit of data to the input key. The 4-bit data is given to the register. The register unit has D flip-flops to store the data. The D flip-flop stores the data and the input of the D flip-flop is given to the output. The clock signal is given as the control signal to the D flip-flop. The output of the D flip-flop never changes until the clock signal is given. According to the configurations of the 16-bit register unit, the output is also 16-bit. The output is divided into 4 subunits. Block processing method is popularly used to derive high throughput hardware structures. It not only provides throughput scalable design but also improves the area delay efficiency. The derivation of block-based FIR structure is straightforward when direct form configuration is used, whereas the transverse form configuration does not directly support block processing, but to take the computational advantage of the MCM, FIR filter is required to be realized by transverse form configuration. Apart from that, transverse form structures are inherently piplined and supposed to offer higher operating frequency to support higher sampling rate. The FIR filter block consists of block multiplication technique and MCM. The FIR filter has multiplier block and also the adder block. The 12th bit of the 16-bit data is multiplied in the multiplier unit, and the 13th bit of the 16-bit data is multiplied in the multiplier 2. The 14th bit of the 16-bit data is multiplied with the 16-bit data in the multiplier third. The 15th bit of the 16-bit data is multiplied in the multiplier 4. The output of the 4 multiplier blocks is given as input to the full order. The full order outputs 16-bit of data. The 16-bit data is divided into 4 subunits. The 16-bit data is divided into 4 units that is given as input to the pipeline order unit. The unit consists of D flip-flops and full orders. The first 4 bits of the 16-bit data is given as input to the D flip-flop and is multiplied with the and is full added with the second subunit of the 16-bit data. The output of the full order is added with the third subunit of the 16-bit data. The output of the D flip-flop, the output of the full order is given as input to the D flip-flop. The output is then full added with the fourth block of the 16-bit data. Finally, we get the 4-bit of data as output. Finally, we are going to see the output for our product. We are using Xilinx 14.2 version. The project, we have to create the new project by clicking on the file and new project, the project source. Then the new source is added for the space for the code. The VHDL option is selected, and the storage area is also selected. For that, we have to click on project and new source. Then we have to simulate the code by clicking on simulate behavior mode. We are seeing the output for our code in iSIM. First, we have to give the values for our product. First, we have to give the reset by clicking on right click and force constant. Initially, we give 1 and click on enter. Then we have to give the clock source. Then leading edge is 0 and trailing edge is 1, and the time period is 1000 nanoseconds. Click on enter. Then we give the input for our product. Then run the product. Initially, the output will be 0 because of the reset condition. When the reset is 1, the output will be 0 again. Then we have to give the reset value as 0. Click on enter. Then we run the program. The output will be passed. The output of the data is displayed by, then the output is the input of the input data is filtered by the FIR filter and is with the better computation level. We have to view the synthesis report by click on implementation and then implementation design. Then we have to click on synthesis report. The synthesis report will be generated. In the synthesis report, we are getting the information about the number of flip-flops used in our product, LUTs and etc. These are the registers, slice registers used, LUTs used, flip-flops used. These are the details that we are getting from the synthesis report. Thanking you.